In this video, we're going to discuss the normal distribution, what it is, how we apply it, and then we're going to work through a few practice examples. So let's go ahead and dive right in. So what is the normal distribution? Well, similar to the uniform distribution, the normal distribution is a continuous probability distribution, meaning that the area underneath the curve is equal to 1, and that the values along the x-axis can assume an infinite number of values. So this is a continuous probability measure instead of something like a discrete probability measure, which we've been working on with the binomial and Poisson distributions. So the first thing to know is that it is a continuous probability model. That is, the area underneath the curve is equal to 1. The second thing to know about the normal distribution is that it is perfectly symmetrical about the mean. So when we draw a line right down the middle, the left side is equal to the right side. You could fold the normal distribution on itself and the left side would equal the right side. Now, knowing that the probability under the area underneath the curve is equal to 1, and knowing that the normal distribution is symmetrical about the mean, we also then know that 50% of our observations occur above the mean and 50% of our observations occur below the mean. We also can apply what's called the 68, 95, 99.7 rule. And what that says is that within plus or minus 1 standard deviation of the mean, we're going to see the central 68% of our observations, right? Plus or minus 1 standard deviation from the mean. Within plus or minus 2 standard deviations, so within minus 2 standard deviations and positive 2 standard deviations, we're going to see the central 95% of our observations. And then within plus or minus 3 standard deviations of the mean, we're going to see the central 99.7% of our observations. Something that's important to note is that these tails continue on virtually into infinity, or until the values no longer make any sense. And what we know is that if 99.7% of observations are between plus or minus 3 standard deviations of the mean, well, that means that there's 0.3% of observations, so 1 minus 0.997 is equal to 0.003, or 0.3%, which means that 0.15% of our observations are above positive 3 standard deviations from the mean, and 0.15% of our observations are below 3 standard deviations from the mean. How do we get 0.15? Well, we already highlighted that there's 0.3% of our observations that are unaccounted for. We know that the left side must equal the right side. In other words, it is symmetrical, so we can simply divide by 2, which gives us 0.15% in each tail. So when might we use the normal distribution? Now that we know some of the basic properties of the normal distribution, let's talk about, well, when would we use this in a real life setting? Well, in many ways, you've been using the normal distribution in your day-to-day life probably since you've been young. This is one of the ways that we can identify what is a quote-unquote unusual observation. So something like heights is typically normally distributed. And this is why when we see somebody who's about average height, we're not that surprised. It happens with fairly regular occurrence. Now, as the person gets taller or shorter, we see fewer of those types of people. So let's just walk through kind of a basic example. So let's imagine that the average height for men is 5'9". So we're going to center our normal distribution around our mean, or our expected values, 5'9". And let's say that our standard deviation is 2 inches, right? I'm just going to make this up. So our value for mu is equal to 5 9, and our standard deviation is equal to 2 inches. Right? Again, I'm just making these numbers up. In a practice problem or a real life problem, you're going to have to calculate your mean and standard deviation. But for this problem, I'm just going to make it up. So if we have an average of 5'9" as heights, plus 2 standard deviations brings us to 5'11", plus another standard deviation gives us 6'1", plus another 2 inches gives us 6'3". In the opposite direction, 5'9" minus 2 inches gives us 5'7", minus 2 inches is 5'5", minus 2 inches is 5'3". So now that we have kind of our standard deviations mapped against our normal distribution here, what can we conclude? Well, we can say that 68% of our population is between 5'7" and 5'11". The central 68% of our observations are between 5'7" and 5'11". How do we get there? Well, plus or minus 1 standard deviation from the mean, we're going to see the central 68% of our observations. So this pink shaded region here. If we wanted to know where do we see the central 95% of our observations, we're going to look to plus or minus 2 standard deviations of the mean, so between 5'5" and 6'1". So this is where the central 95% of people would fall, or somewhere between 5'5" and 6'1". And then finally, if we wanted to know where 99.7% of our population falls, well, that's plus or minus 3 standard deviations of the mean in a normal distribution. So between 5'3" and 6'3". So in knowing that we have this 68, 95, 99.7 rule, we can also break down our normal distribution without any calculations at all. Of course, we'll get to how do you calculate probabilities in a normal distribution, but for now, let's just admire the properties that, that the normal distribution is perfectly symmetrical about our mean. So if this is our mean, right here, right? Again, we're centered around our mean. And what do we see? We see that within plus or minus 1 standard deviation of the mean, so from -1 standard deviations from the mean to +1 standard deviations from the mean, we see 34% on each side. So 0.34 plus 0.34 is equal to 0.68, right? Again, this is just showing that our between plus or minus 1 standard deviations of the mean, we see 68% of our observations. Between plus or minus 2 standard deviations of the mean, well, we have 68% plus 13.6 plus 13.6, which is going to give us about 95%. Right? We can get more specific with the decimal points, but for the sake of this video, we're just going to refer to it as the 68, 95, 99.7 rule. And then finally, within plus or minus 3 standard deviations of the mean, if we were to add up all these values, 99.7% of our observations. So what are we highlighting here? Well, we're highlighting that if you break this down, each one of these values is exactly the same. In other words, the area underneath the curve for that particular section is exactly the same. And that's because our normal distribution is perfectly symmetrical about our mean. Now, beyond the normal distribution, we can also break it down into what is called a standard normal distribution. And this is where what you may have heard of z-scores start to come into account. So in a standard normal distribution, our normal distribution is centered around the z-score of 0. with a standard deviation of 1. So 1, 2, 3, negative 1, 2, 3. Again, these tails continue on into infinity, but we're not going to worry about that. So still, within our standard normal curve, it's all the same properties of our normal distribution. So within plus or minus 1 standard deviation of the mean, we see our central 68% of our observations. Within minus 2 standard deviations and positive 2 standard deviations, we see 95% of our central observations. And between negative 3 standard deviations and positive 3 standard deviations, we see our 99.7% of our observations. So same thing is that we're central, or we're centered at our mean. So that means that 50% of our observations are above the mean. 50% of our observations are above the mean. And if we go the other way, 50% of our observations are below the mean. So 50% of our observations are below the mean. We'll learn more about the standard normal distribution as we go today. But when we look at what's on our x-axis here, our z-score, we need to be focused on how do we calculate that z-score. So our calculation for our z-score is simply this equation right here. So z is equal to the observed value of x minus the expected value of x divided by our standard deviation of x. Okay, that's how we calculate our z-score. Now, you can use this equation. It's called the standard normal density function. This will help you find the area underneath the curve. Although truthfully, you never need to use this equation because you usually will have access to either computation or a Z table. And today we'll work through how to use a Z table. So that's enough talking. Let's dive into a practice problem. So here's our practice problem. The Environmental Protection Agency's fuel economy estimates for automobiles suggest a mean of 24.8 miles per gallon and a standard deviation of 6.2 miles per gallon. For highway driving, assume a normal model can be applied. So the first question here is draw the model for auto fuel economy. Clearly label it, showing the 68, 95, 99.7 rule about miles per gallon. Okay, so let's go ahead and do that. So let's first draw our axes. So we're just going to put some kind of function of x on our x-axis, and then we're going to have our values of x on our x-axis. And then we're going to draw our normal distribution. It looks like this. And then what are we given in the question? Well, we're told that we have a mean of 24.8 miles per gallon and a standard deviation of 6.2. So let's just write these right here. So x bar is equal to 24.8 miles per gallon, and our standard deviation is equal to 6.2 miles per gallon. Okay, so in our normal distribution, we know that we're centered about our mean, so we're going to say that this is about center. So 24.8 is our mean. And then we're going to go ahead and we're going to say plus 1 standard deviation, so 24.8 plus 6.2. So 24.8 plus 6.2 gives us 31. Plus 6.2 is 37.2 plus 6.2, which gives us 43.4. In the opposite direction, 1 standard deviation below our mean, so 24.8 minus 6.2 gives us 18.6. Minus 6.2 gives us 12.4. Minus 6.2 gives us 6.2. Okay, so that's our basic labeling. Now we have to show the 68, 95, 99.7 rule. So let's just get another color here. So our 68%, central 68% of our observations are between -1 and +1 standard deviations of the mean, so between 18.6 and 31 miles per gallon, so 68%. We have 95% of our central observations are between -2 standard deviations and +2 standard deviations. So between +2 standard deviations and -2 standard deviations of the mean, we're going to see 95% of our observations. And then between ±3 standard deviations from the mean, we'll see our central 99.7% of our observations. Okay, so that question for A is now done. Let's move on to B. In what interval would you expect the central 68% of automobiles to be found? Well, in that case, we have already completed that because we've labeled our graph up here. So the central 68% of our observations, we expect to find between -1 and +1 standard deviations from the mean, and otherwise between 18.6 and 31 miles per gallon. So we can write that out. So we'll just say B. The central 68% of observations will be the mean plus or minus 1 standard deviation, which is equal to 18.6 and 31. So that's the interval in which we would expect to see our central 68% of our observations. About what percentage of automobiles should get more than 31 miles per gallon? Okay, so there's a couple different ways we can answer this question, but let's go ahead and answer it the way that we're going to do in this question. So let's just draw it out and make our lives a little bit easier, just because we're not dealing with writing over top. So we know that we're centered around 24.8 miles per gallon. And we know that 31 miles per gallon is 1 standard deviation from the mean, but let's pretend that we don't know that for a second. So what are we interested in? We're interested in what is the probability that they get more than 31 miles per gallon, and otherwise known as this yellow shaded region to the right. So let's go ahead and calculate a z-score. So z is equal to the observed value of x minus the expected value of x divided by our standard deviation of x. So 31 minus 24.8, right? Our observed value minus our expected value divided by our standard deviation, which we're told is 6.2. So 31 minus 24.8 is 6.2 divided by 6.2 gives us a z-score of 1. So we can look at this and we can draw our standard normal distribution. And in our standard normal distribution, we're centered around a z-score of 0. And what we have here is a z-score of 1. So we're also interested in, again, the area to the right of this. So this yellow shaded region here. So the probability that z is greater than or equal to 1 is equal to 1 minus the probability that z is less than or equal to 1. Now, what is the probability of that? Well, in this case, we're going to go to our z table. So this is what your z table might look like. It's going to look something like this. So we're going to go and we're going to find our z-score of 1. In this case, we can find that right here. I'll just try and get a color here so I can show you. The z-score of 1. And we're going to look for 1.0, which is right here. So our z-score is has a probability of the area to the left of the z-score of 0.84134. So we'll go back to our thing. So 1 minus 0.84134, which was the area that was presented in our z table, and we'll just double check. 0.84134. Yep, so we're right. So 1 minus 0.84134 gives us 0.15866. Okay, so there we have finally completed question C. In question D, what percentage of cars should get between 31 and 37.2 miles per gallon? Well, there's a long way and a short way to do this. In this case, we can break it down. We can remember here that, we'll just draw it back out down here. This is D. We have our normal distribution. Again, we're centered around 24.8 miles per gallon. And then we have our standard deviation. So this was 31 miles per gallon. And then the next one was 37.2 miles per gallon. And the question is asking us, what is the percentage of cars that should get between 31 and 37.2 miles per gallon? So there is a short way where you could use the knowledge that it's symmetrical in the 68, 95, 99.7 rule. But let's go ahead and do it a bit of a longer way. So let's go ahead and calculate z-scores for each one of these values. So we already know that z is equal to the observed value of x minus the expected value of x divided by the standard deviation of x. So 31 minus 24.8 divided by 6.2. This gives us a z-score of 1, as we've already identified. Now our z-score associated with a value of 37.2, so 37.2 minus 24.8 divided by 6.2 gives us a z-score of 2. So we want to know what is the probability that is within these shaded regions. So we're going to say the probability that 31 is less than or equal to x, less than or equal to 37.2 is equal to the probability that z is less than or equal to 2 minus the probability that z is less than or equal to 1. By doing that, we're going to get this nice yellow shaded region here. So we can go to our z table. So the probability that z is less than or equal to a value of 2. Whoops. So our value here for z is equal to 2. 0.97725. So 0.97725 minus the probability that z is less than or equal to 1, which is right here, 0.84134. 0.84134. So we can go ahead and do that math. So 0.97725 0.7725 minus 0.84134 gives us 0.1351. Okay, 0.1351. We'll go back to our graph here. It's a very close to 13.6. In fact, you would round that to 13.6%, and that is exactly this region that we just calculated right here. So between +1 standard deviations and +2 standard deviations, I'm showing you that you could have hacked it using this this knowledge of your normal distribution, but we decided to practice calculating the z-scores. And then finally, describe the gas mileage of the worst 2.5% of all cars. Okay, so this is a little bit different. The worst 2.5%. So let's go ahead and draw it out. We have our normal distribution. Again, we're centered around 24.8 miles per gallon. And in this case, we're interested in the worst 2.5% of all cars. In other words, the area underneath the curve here, the worst 2.5%, so that's the area to the left, is equal to 0.025. So we don't know what this associated z-score may be, or value of x. So let's go ahead and look up that probability in our z table. So we're going to find the z-score associated with 0.025. So we look here, and we're looking for 0.025. And here it is. So our z-score in this case is negative 1.96. Oops. Right? This is where it all intersects. Negative 1.96 gives us 0.025 to the left. So we can do this. So z is equal to the observed value minus the expected value divided by the standard deviation of x. So we know that z is equal to negative 1.96. We don't know our value for x, but we still know that it's centered around 24.8. We know that we have a standard deviation of 6.2. So 6.2 times negative 1.96 is equal to x minus 24.8. So 6.2 times negative 1.96 gives us negative 12.152 plus 24.8, which gives us our value for x. So 12.648 is equal to x. In other words, the worst 2.5% of all cars will have 12.648 miles per gallon or less. And just like that, we have done our introduction to our normal distribution. We've learned about the standard normal distribution, and we've learned how to calculate and derive probabilities from z-scores. That's it for this video, but if you found that it helped to make statistics easy, consider showing your support by giving the video a like. And if you still need more help with statistics, then consider subscribing to the channel if you haven't already. I look forward to solving many more problems with you next time.